This is week 9 of Stochastic Control and Communication, and I am Apurva. So, let's take a quick recap of what we have done so far. Um, like I had mentioned last time, this is going to be slightly different trajectory, different route from now onwards. So, in the whole work of stochastic control, we started by defining what is a stochastic control problem or what is an MDP. Then we talked about what kind of policies are possible, as in what kind of actions are supposed to be taken and what does a policy mean. We saw a few different types of policies. So we saw Markov deterministic, Markov random, history dependent deterministic, history dependent randomized. And one of the things that we found out was in regular problems, Markov deterministic is actually enough. That is because of the structure of a standard control problem or a Bellman equation, uh, the structure of the additive structure of Bellman equation. Then we talked about, we saw a lot of examples of the same thing. Then we talked about what happens if we have imperfect information, meaning there are some observations made and those observations may be noisy observations of the true state, or there is something else included in it, so we don't know the actual state of the system. If that is the kind of situation, or what we called as partially observed MDPs, there the history mattered. So we defined the state, we defined a new state which was basically the information available at any time step k, and that's what was expanding. And we talked about how this reduces a POM-DP to just an MDP itself, and we can apply all the other rules, all the other things that we know about MDPs. In that sense, still a Markov deterministic policy is being used, but the state itself is something which is history dependent. Then we studied this in way more detail. One of the common examples that we saw in both of these settings was linear dynamics, quadratic gain, and some kind of noise. Either it was just standard without taking any particular form of it, or letting the noise be Gaussian. So these were some of the things that we saw. And in LQG problems, there was one more very interesting and fascinating result that came up. In LQG, we saw, this is not specific to LQG for now, it's specific to LQ control problems. We saw problem with noise or problem without noise have the same optimal strategy or the same optimal actions. And if instead of being in the situation with perfect information, if we were suppose in the situation with imperfect information, then the optimal action has the same component. So here the optimal action uk would have some lk times xk. Same thing would be here. In case of perfect information, the uk would be lk times the belief about xk given the information ik at that point of time. So because of this particular result, that we can find this LK from a simpler version of the problem, whether LQG or not, but LQ at least, and we can have a separation between the controller version and the estimation version, gave us a separation principle, gave us a few nice results. And from that point, it seemed that it might be something that is general, it might be something that is common across different problems, at least of the kind where you have linear dynamics and quadratic cost. Today, we'll see that that's not always the case, and we'll go through one of the counter examples to this idea. But before we get to that, one of the things that was assumed here was how the information was growing. So, if you recall, the information was, in case of imperfect information, so the information was ik, let's say, the dynamics of the problem is something of this form. And there's some noise, wk is the noise component, and yk refers to the observations yk plus 1, and that is some gk function of xk plus 1 and some noise component, whatever that function may be. If it's linear, it all turns out to be some linear function of all these things. The typical thing was the information available at time k plus 1, for example, was the observations starting from y equal to 0 till y equal to k plus 1, and actions starting from 0 till the last action which was taken. The current action is yet to be taken. So it is up till uk. And this means we could write ik plus 1 as whatever was the information available at ik, and along with that just take the union of these two terms and we are done. Which means ik plus 1 is a superset of ik. Here the inequality doesn't exist, but in general they might even be equal for certain k values. But k plus 1 will have more information than what is available at k. So this type of partitioning in information is what is called as classical information structure. And whatever we knew about LQG or LQ problems, part of that was happening because of this type of a structure. And the word information structure means what is known to each of the people involved, or each of the agents involved, or each of the controllers involved. So it's just who knows what at any given time instance. So at any time instant. Now let's try and understand what does this mean. How can we understand this type of an information structure, and then we'll see a few examples before we go on and talk about non-classical information structure also. So this means, so let's say we start at time k equal to 0. So at time k equal to 0, ik would have, or I0 would rather be the observation y0. At k plus 1, it will get added with more information, so it will have y0, y1 and u0, and so on. It will keep on continuing this way. But in the perspective that we think of as one controller or one agent taking actions again and again, meaning taking controls again and again, if that's the kind of perspective we are sticking with. So I'm talking about the scenario where we think of this as there's one agent or one player that takes multiple controls, meaning each kth control refers to the kth time the controller is taking a control. The first one, second one, until whatever horizon that we've kept. To be able to say that I k plus 1 is a superset of I k is like saying this information needs to be stored somewhere. First this one, then this one, and so on. All of these information need to be stored somewhere. To be fair, it is enough to just store the very last one for whatever is the time horizon. So let's say k equal to n. Whatever that is enough. But that would have grown quite a lot as compared to whatever was the information in the beginning. If that is the case, to store such a huge amount of information, it requires a lot of storage capacity also. So, in some sense, this condition this particular criteria, this kind of a pattern between information, requires that there is infinite amount of storage available. That's the first perspective of thinking about what happens in standard situations that we have seen so far. Most of the situations we've seen so far were of this kind. But that's not the only way to think about it. So, another perspective is we can think of this as multiple agents or controllers, each taking action at one time step. If that is the case, then notice what this would mean. There's ik and there is ik plus 1. So if ik and ik plus 1 refers to the kth agent or kth controller versus the k plus 1th controller or agent, then ensuring this condition means whatever information was available up till ik, that needs to be transferred to the next controller or the next agent. Along with that, it will get more information. So whatever was here, that is going. Along with that, some new information is getting added on. The new information would be the observations of the next step and the action taken at the current step. So this is a situation with perfect communication between the controllers. So even though this underlying assumption of classical information structure seems valid, this may not always be true, because both of these perspectives of thinking about this information structure, this is not very natural. We will not have unlimited or infinite storage. There is going to be a limit to how much storage is available. There might be a budget to how much storage is available. That's one way of thinking about it. Another is, if it is some information that is passed on from one controller to another, then passing on of information may not be noiseless. There may be some noise involved. If that is the case, this may not be perfect communication. There may be there may be steps needed to make it into as perfect as possible. But by default, it won't be perfect information or perfect communication. So this is to point
Do we
out. Sorry, yes.
any do we have any example of multi-agent in real life? Because I'm not able to like visualize like where we'll apply and where the communication problem comes. Because for our case in industry, we have one single controller enough to do, or its versions. But where this communication problem comes,
So, so I'll give the same example that Sir gave, and in giving that example, I'll answer your question. Okay. So
yeah, perfect.
it's just a perspective. First of all, multiple controller means there is more than one decision problem to be solved. There are more than one set of actions to be taken at different stages. And if there are stages, then you can't always assume that if you solve the best one at one stage, you're done and you don't need to worry about the next stage. If that information has to be passed on to the next one also. So, for example, right, this was the example even Sir talked about in the lectures. So, consider a scenario where there's a system, there is there's some sort of a connected actuator, or maybe it's like maybe your system is like the environment and you have a robotic arm trying to move around the area, maybe pick up something. So it's not a learning problem, it's a control problem, just remember that. So if there is a system or there is some environment, that means there is going to be some sensors to take readings and observations. Once the readings and observations are taken, those will be used by the controller to decide what to do next. Now, typically, the system and the actuator would be connected to each other, as in physically connected to each other. This may be something that we can't actually draw a separation between. But controller might be a computing resource that may not be necessarily physically connected to the main system. Okay, so now we clearly know that this is one of the spots where a decision is to be taken, right? But now, to give the interpretation more clearly, think more specifically of this particular section where readings and observations are being taken. Whatever reading and observation is being taken, that is getting passed on to a controller, right? So, in some sense, you can think of it this way, that what is observed by the sensor, there is some amount of decision to be taken at this level as to how do you modulate or how do you regulate the observation itself before you pass it on to the controller, the decision maker. So in that sense, uh, so now think of this entity, the reading component, also to have a decision type role, meaning the observations are to be, there is some optimization happening. So it's in the sense that suppose you took readings and you took three or four readings of the same thing. From those three or four readings, now you're supposed to decide which observation do you tell to the controller. Do you tell all four of them? Do you tell maybe some sort of a moment type information about it, some statistics type information about it? Or do you apply a function on top of it and then tell it to the controller? All of those decisions, all of those options are available to the this particular section, the portion where readings and observations are being taken. right?
So
So
in that case, we have to communicate also which what I'm going to convey to controller.
yeah, exactly, so that will
Um,
also come up. So now these two are like two decision makers right now. And just like you said, because there is now a need for passing on the information, there may be a communication medium which in general is not going to be which in general is not going to be noiseless, meaning you'll have to even worry about that. So there may be a transmitter and a receiver. So this is the communication channel or the communication medium. So now this got converted into the above problem where we had only one decision maker. If we think about it more carefully, this actually has more than one decision makers. There is a decision here, there's a decision here also. In the sense, how do you receive the information? Do you let some modulation happen? Do you encode it, and then after it has passed through the channel, do you, after having received it from the receiver, do you decode it? Encoder decoder is also one more component, but that one I'm not is worrying about too much, and I'm assuming that is already a part of the transmitter and the receiver themselves. Meaning, this problem, if we think slightly more carefully about it, it is a problem with multiple decision entities, and all of these decision entities are sequential. All of these decisions are to be taken in a sequential manner, and in that sense, the information that passes from here till here, if it is perfect information, then we can say that the kind of classical information structure can be true in general. Otherwise, that's not the case. And we don't have to even try to justify it, because here, if there is a communication channel and there is a communication medium from which the readings are being transmitted to the controller, there'll be some loss by default. So if I just want to compare these two, so let's say this is I1 and this is 2, this is 3, and this is 4. So by classical information structure, I4 should definitely be bigger than I1. But because of lossy communication, and this is what we expect or we want this, but in reality what we'll get is I4 may not even be may not be more than I1. It may not know all of I1. In fact, some of it will get lost because of the presence of communication in between. Does that clarify what you were asking?
but in that case, this will be problem of communication infrastructure. If something get lost, the information transmitted or this received.
Yeah, sure, it is, of course. But what I'm saying is, I am treating all of these as some or the other decision problems. If you don't like this component, don't worry about it. Just compare the reading, the observations part, and the controller's step. Meaning, I'm saying that those two are definitely clear cut decision problems. Typically, if you recall, here when we talked about LQG problems, we were talking about a separation between the controller and the estimator. And this type of a separation is generally used. Different components are designed separately and then put together, expecting that even together they'll work in an optimal fashion. That their individual optimal points, optimal behaviors would turn up to give an overall optimal behavior also. That may not be true in general. That is the same point that is coming over here in this example also.
Okay, I had like something to convince myself when I was reading this.
Mm-hmm.
It's like suppose we are using Google Map and to go, for example, IIT Bombay to some place. Now that is orange showing me. but it's actually red or maybe green. There is no orange something. So is that considered to be in that case? Because I can assume controller will be like me. I am deciding my car, and reader will be that Google whatever GPS systems are, and communication is the app medium through which I am. They are communicating with me, or maybe there is a pothole which is creating a traffic jam, a phantom jam.
I think that's
Is
a good example. So we don't have to worry about the communication medium here because you're just looking at your phone's app and you're deciphering what it is telling you. But inside the observations that are being projected by the algorithm of your app, there is definitely some optimization, some decision that is being taken. So typically, a Google map in deciding whether a particular road has too much traffic or it is less traffic or it has no traffic whatsoever is done by just one second. Yeah. Uh, Whether there is traffic or not, that is decided based on maybe the number of active cell phones in a particular range. If the number is more than a threshold of theirs, then it is given a certain color. My guess is that's how it gets decided. But
almost.
that is a very dynamic situation that is happening over a period of time. Traffic is moving, meaning the system itself is evolving over time. So along with that, the observations that it is showing should also evolve, but that evolving behavior may not be visible to a controller in real time. So at any given
Mm.
time instant it might not be known to you that,
Yes, exactly.
just like for example there could be a pothole. So yeah, I think that example captures it very well. That captures the exact scenario we're trying to discuss through this example.
But there is a catch in this example. I don't know, did you catch this thing or not?
Hmm.
The catch here is the system and controller are same. Like if you see, I am a car driver and I'm only the controller. I am the system actually.
You're not the
So
system. You're not the only system. See, you are one entity in the system. There are others. In a traffic situation, there are other cars on the road. There are other. There might be animals crossing. There might be potholes. There might be the environment itself, the road itself. That all of that together is part of the system. You don't have control over all of those things. You have control over only on a limited thing. So, for example, your own vehicle.
mhm. Okay.
So when we talk about system, we have in our background, we're saying that there is some environment that we have no control over. That's what we're trying to sense and observe and make readings about. That's
Correct.
where this component comes in. Like from system we make some observations, but there's something that we are sensing and making observations about. There's some state of the world.
Okay, so the entire road is the system.
Yeah.
Then the
So
some GPS reading is this reading sensing, and then controller is me. In between the communication is the app.
so this is like the reading and all of that is done by something, I don't know, maybe GPS or something. There's something that observes. Then the communication to you is through the app. Then you as the driver is the controller. So that's the driver. As a controller, what you're doing is you're steering the wheel, you're deciding to brake or not. So that component is what gets affected by your decision of what to do. Maybe if you don't want to think about yourself as the driver, you can think of uh, automated autonomous vehicle as well. So here there might be a wheel to steer or some actuator.
Mm-hmm.
And again, the system is the whole thing. It consists of the road, it consists of other vehicles,
But but
the
but
whole
but
environment.
if you consider this as a road, then the controllers will be so many cars because I will not be the lone driver there.
Yeah,
So this
that's
app is communicating to all the drivers.
hmm. Now, that's a multi-agent problem, and we are thinking of ourselves as the only agent and everything else as a part of the system or a part of the environment. which we don't have control over. It's
Okay.
like a field theory view. So it's a standard view to, think about multi agent type systems if you can't directly work with them. So as a view, as an interpretation, it's okay. There's a slight subtlety, but it's still not a very big issue. And
Okay.
then here you're making, using your sensors and so on, and making observations. So there are two decision entities. So there are two places where something is happening. Here, when I say the GPS, it means the GPS of one car, but it might also be using all of the other GPSs and all of the
Whole-
information. That is hard to capture here, but there's some way of getting the reading. This may not be the best way of putting it.
the whole system reading.
Yeah, it's whole system reading. So it's just some kind of reading. How that reading is taken, we know that there is definitely some algorithm these apps are using.
Mhm.
Fine.
Yep. So
So,
basically, real-time data is not properly shared. That is I4, not superset of I. Okay.
or there might be a delay.
Yeah, I'm feeling like this is
Something
a
may have
delay.
happened here, but it may not have gotten sensed. By the time it gets sensed, previous would have reached you. So the current information and your information would have some sort of a lag, and that could create,
Phantom traffic.
yeah, that
But
creates lack of information. That creates difference in information.
but when sir was telling communication problem, being from communication industry, I felt very bad. I'm like, no, it did not be because we have so much robust system. It cannot. Only the delay is the potential problem. Okay, because we have very solid systems for communicate.
I don't think he was saying it to point out that communication systems are not strong enough. It's just that no matter how strong any given robust communication system is, you can't expect it to give noiseless communication over any particular channel.
True,
It's
true.
probably just in that sense and nothing more than that. So that's a very simplified view of the whole thing. Okay. So with this we have talked about what is classical information structure, then what is an example of something that is not classical, something slightly realistic as an example, and now we'll take a few more examples of classical information structure only. Like, it can have a lot of variations. Let's first look at that and then go to non-classical again. Okay, so let's take a few examples. These are all examples of classical information structure. Remember, the idea is very simple. Ik should be a subset of ik plus 1. That's all. That's the only requirement. So, one scenario is, suppose the one that we have always seen. So, ik is y is referred to the observations here. Okay. So, y starting from 0 till uh, you will have observation of the current state, but you will not have the observation, the action of the current state. K minus 1. So this is a standard information structure, a standard example of classical information structure. Like, here it's very easy to prove that k plus 1 would have k and with that it will have yk plus 1 and uk. So by default ik is a subset of ik plus 1. So this is definitely classical. This is like the whole thing. Now another variation could be that there is a situation where the information, the ik information only has information about the observations and it knows nothing about the actions. That is also a valid ik. So ik is just all the observations. So this is just the observations. Here again we can easily show that ik plus 1 would be a superset of ik. So again this is going to be classical. Alright, what about a situation like this? Let's define the dynamics first. So let's say the dynamics is xk plus uk. Okay, and I am not including any observations as of now, so it's a simpler situation. I0 is just x0, ik is xk, u0 till uk minus 1. Is this classical or not, and how do you justify that? So if you directly look at it, ik plus 1 would have xk plus 1 and this. So if we just directly compare, there is a difference in these two informations. It doesn't look like they're related to each other, but the catch is in the dynamics itself. The way the dynamics is defined uh, makes it useful. So consider the dynamics carefully. So xk is equal to xk plus 1, meaning if I know this and this, I actually have managed to find this as well. So in short, if you now compare ik plus 1 and ik, which has more information, which has more, which is a subset here?
Ik is the subset of ik plus 1.
Ik is the subset. And we were able to do this because the dynamics is very simple and there are no observations in between. Now let's take another simpler example. Oh, okay, there is some space. Let's take the same scenario, but maybe let's do it this way. What about in such a scenario?
But y0 may not be defined, right?
So the way I've defined it, y0 might just be equal to x0.
Okay. So observation is equal to real state.
Yeah. I actually
Okay.
didn't do anything. It's the same as the previous one. Observations are like just added information. So it has all of it.
Mm-hmm.
Just a convoluted way of saying it. It's the same thing. So
Mm-hmm.
in reality, what is happening here is these two are the same things. So this and this are the same things.
Mm-hmm.
So I0, I1, I2, whatever, all of these have some redundant information. But nevertheless, they still follow the classical information structure. So ik plus 1 would still be this way. Right now, let's take this case. What would happen if I add some noise here? So rest of it is same. What happens now? Same I0 and IK as before.
So x0 is missing in IQ.
So we can just try and compare I0 and I1, right? And that'll give us the answer. So I1 would be x1, y0, y1. Can you use similar logic as before? So can you write x1 minus u0 as x0?
Okay. So the classical information need not be exactly there. It can be derived.
Yeah, that's what we did in this example also, right? In this example also we did that exact same thing.
Okay.
It can be derived maybe in a direct fashion, maybe through observations. In the last example, the observations were the true information themselves, so there was nothing to worry about. Here the observations are noisy, so from here we would actually be able to even tell what are the respective vks. Do you see what I'm saying? So from
Yes,
here
yes, yes.
we
Subtract it simply.
yeah, exactly. So now that we know x0, we know x1 and y0, we know all of these things. So for us, y1 is just y0 is x0 plus v0. So now we know what exact noise got added. So the whole game here is depending on what kind of information structure you're getting, the situation changes. Now, okay, same thing. Now, it's just that we're looking at different variations of this, but nevertheless, the point of giving these examples is uh, information. Any particular choice of information doesn't have to be what is something that we've seen in a standard way. Nothing is restricting us to look at other ways of passing on information. Okay, so another possibility could be if I have the same dynamics as a box, but now my I0 only has Y0 and my IK has Y0 till YK, U0 till UK minus 1. Now what?
But in previous example, I2 is not fitting, right?
I2 is not
If
fitting?
if you have I2,
Hmm.
we will be having X2, but X1 is not there. To derive this, we need to subtract the mu, the u.
Okay, hold on. Let's try that out then if you're not sure, if you're not convinced yet. So, you're convinced that I1 has more than I0. Okay,
Okay,
this
got it.
part you're convinced with. Let's try out I2. I2 would have X2.
No, got it, got it. This is got it. There is no noise in the X, that's why it's possible. Yeah,
We would have the action. We would have the action available. That's
action
why
available.
we'd be able to remove from that.
Yes, yes.
Yeah, again, dynamics has no noise. That's definitely there. So
Mhm.
it'd be something like this. So we'll start from y0, we'll have till y2. Now we'll be using these two.
My mistake, my mistake. It's
So
possible.
yeah, yeah, yeah. No issues. It's better that you get convinced rather than still not sure, still have some confusions left. Okay, what about this sixth scenario that we're looking at now? Same dynamics. I've not changed the dynamics. All I'm changing is what kind of information is available at each time step. Okay, let's write down I1. I1 would be Y0, Y1, and U1, which means I know this, I know this. Can that help me deduce anything about the x's?
To noise, no.
It doesn't let me know about the x's, but I0 is still a subset of I1. That was the only requirement.
Okay, okay.
So
Correct.
you're understanding, right? The whole game ends up being you have to focus on this simple relationship. Does this hold or not? This is it. And this relation should hold for all k.
Okay. For all.
That's it. There may be certain case for which it might hold just as an equality. It's fine. But as long as this holds, we're fine. What could have changed is if suppose no, not really. So one scenario could be, now this is, I'll stop with this scenario and not go any further. Let's say we have xk plus 1 as some xk plus uk. This is still nice, okay? Now, remember what we're supposed to look for. This is all we're supposed to look for.
Yeah, definitely it's non-classical.
It's non classical. And in the counter example that we'll see, the information structure is somewhat of this kind. It doesn't even bother having use, it stops with just one observation at each time step. And you can't deduce anything about the previous one or something about the previous one from the current one you have and all of that. Okay? So now let's move forward. Now, before we go into the details of what this counterexample is focusing on, um, remember whatever we know about linear quadratic systems. In linear quadratic systems, we made a few very strong statements. We talked about um, principle of separation between the controller and the estimation problem. Then we also said that if we have a Gaussian setting, if the noises and the initial state were all Gaussians, independent Gaussians, then that estimation problem will just be linear in whatever information was used. So there is a linearity in the optimal actions for each time step k. Witsenhausen's counterexample will basically be saying that this linear optimal strategy may not hold if you are outside the region of classical information structure, and that all of those certainty equivalence principle, separation principle, they may not hold outside of classical information structure. So the assumption of the information structure which was underlying in LQG problems and other problems is being brought to light through this example. That's the core idea. And the problem itself is very simple, but yet giving a proper answer to it, giving an optimal to this, is still like an open question as far as I am aware about it. So let's go through the details of the problem. So this problem can have a few interpretations. We'll go through the interpretations slowly, but for now, let's just focus on the core mathematical points here. So here we have some state x0, the initial state. There is an observation made about that. The original observation y0 is just x0 itself. Then x0 is added with some action that creates the next state x1. But the observation is not of x1 on its own. There is some noise that gets added to the point where observation is made. So y1 is no longer a noiseless observation. Then the controller is supposed to take action u2 based on whatever it has seen up till now. So there are two controllers here. Controller 1 is u1 and the other controller is u2. u1 is going to make actions up till here, u2 is going to make actions up till here. And after u2 is also taken, the action is taken, the next state is created. And the cost for this problem is similar to a standard Gaussian cost. There's some constant, there's a u1 square term and there's a x2 square term. So there is a square on this and a square on this. Those are the only terms. Typically, LQG problems or LQ problems can have other cost terms also. This one has just very specific cost terms and it is discarding the other ones. Another thing to note here is the x0 and v. So both this quantity and this are taken to be Gaussian and independent. Anyways, we'll not get to using that, but we're just being told that's what it is. Now, the information structure of this problem, the information available to each controller before choosing their actions is u1. It's available at this point. So u1 is just y0, and what is available right before u2 as I2 is just y1. So clearly this is a non-classical information structure. Right. So now, what exactly is the problem in this kind of a situation? So let's focus on the sorry. Um, right. Let's focus on the optimization problem here. The optimization problem is to minimize and in the process of minimizing we're supposed to find the optimal policies. So let's say the optimal policies are u1 star, or u1 is some function of information available up till that point. Okay, it's denoted by I1, and u2 is based on information available at that point, whatever that function is. So now this is an optimization over the functions, because we can't assume that the functions have to be linear in the information. Okay, let's write out these terms slightly more carefully. u1 is gamma 1 square of I1, and x2 is something that depends on x1 and u1. So now if we only focus on the problem available to controller 2, meaning if we only focus on this part, then this component is basically it's supposed to minimize over gamma 2 quantity like this. If I don't make any assumptions about what kind of whether x1 and all these are scalars or vectors, then I should be rather taking the L2 norm here. And we already know how to deal with this. This is a standard problem. This is problem of minimizing the least square error. And we know that the solution to this, the gamma 2 star, would be this is this is the part that we talked about in the estimation problem also. So that's the same thing over here also. There is a catch, but for now we can just notice that there are similarities. Okay, any questions up till now?
No.
Okay, so if you were to write out the whole optimization problem with this in mind, then that is okay. Let's say we have fixed gamma 1. For the first term, it just depends on gamma 1 only, so there's nothing to be minimized over with respect to gamma 2. The second term needs to have that effect, right? And this becomes minimization of, not minimization, I'm saying I've already minimized and I got gamma 2 star as x1 minus whatever gamma 2 star. So right now I'm not saying anything about whether there is any dependence of gamma 1 that shows up here or not. For now, I'm not saying any of that. Typically, if we are talking about such a situation, gamma 2 will just be a function of I2. But it is very much possible that I2 might itself be a function of gamma 1. So let's focus on that part now. Uh, Maybe let's do that right here. So let's write out what are both of these things. X1 is x0 plus u1 and y1 is x1 plus v. So this is basically trying to estimate x1 having a noisy observation y1 which is x1 plus some noise component. But notice this x1 is something that depends on the action taken by the previous controller, so it depends on u1. This is, to be more specific, it is x0 plus whatever was done by gamma 1 based on information it saw. So let me just let it be gamma 1 for the time being. Gamma 1 depends on x0. Gamma 1 is found at this stage. So all it has seen is either x0 or y0, which happens to be the same thing. Then it's being conditioned on so because of this dependence, this gamma 1 coming up here, which is what we have fixed while doing this optimization, meaning this is something controller 1 has to make a plan about. What kind of information should it pass on to the next controller so that the next controller can ultimately take an action such that this gets optimized. whatever is the cost gets minimized to the best possible value. So controller 1 has to not only think about his own action, but he has to try and think about how his action would affect the actions that can be possibly taken by the next guy also, the next controller also. So this becomes a highly non-linear problem in the sense now gamma 2 star will definitely depend on gamma 1. It has dependence on all of these, but the focus here is gamma 1 because we're minimizing over gamma 1 out on the outside. So let me write this more carefully now. This is k square x1 square. This is just depends on x0, so not an issue. And this component, solving just this is not very difficult for gamma 1, the controller, the first controller. But having to consider this possibility also is quite tricky because now gamma 1's dependence is inside the gamma 2 star function, and this is highly nonlinear. And all of this happened because we are dealing with a non-classical information structure. But recall the problem at hand is something very simple. We have only taken 3 time steps, 2 observations, everything linear, everything fairly simple. The information available is just the observations, and yet the optimization problem specifically for controller 1 is turning into something non-linear. Oh, okay. I already talked about all of these things. Anyway. So the point is, it may not be possible that the optimal strategy for U1 or the optimal policy for U1 to be something that is linear in x0, because it's not taking the decision only in terms of x0. It has to also consider what will happen to what is done by the next controller. Now, recall the reason why this is more complicated than what we had in case of the previous situation, the LQ or the LQG problems. The main thing was, in that scenario we were only talking about actions. Here we are restricted to talk about the whole policy, the policy as a whole, the whole thing.
But if policy is fixed, it will boils down to action, right?
Yes, but now the policy means it's a function, and I
Mm.
just showed you here it's a function of a function. So if you want to calculate what is gamma 2 star gamma 1 for any particular input value, you need to know the whole of gamma 1. You need to know the full function gamma 1.
Gamma
Only,
1 of the state, all possible state.
yeah, because that is what will be used by controller 2 to choose its complete action. So there's like a asymmetry in the problem that is available to both of them. For
Uh,
agent
mhm.
2 or the controller 2, The problem is slightly simple in the sense it just has to do this based on whatever information it got. The information it got is anyways limited. But
Mhm.
controller 1 ends up having to solve a very complicated problem.
Yes. I just last 2 days I've been wondering on this guy Westinhausen.
Mm-hmm.
Like these things were very easily visible with us till now, but I was not able to think. After this, it's making common sense. Like really, the influence of the past action has a impact on the next action. Like, but how he has thought the first time, it's very beautiful in itself.
Yeah, I mean, it's still like a landmark result. I think this is what Sir was also telling, right? Still, people have not managed to come up with a standard way for solving this highly non-linear problem. So
We don't have solution, but we can
it
solve,
was
right?
numerically maybe, but
Okay.
being able to say that okay, you should look at this class of functions to find
Hmm.
your optimal strategy in such problems. Maybe that's what is not found yet.
Okay.
Sorry. So it's true in most of the big research ideas or big research things. They seem, in hindsight, they seem obvious. They start to seem okay, that makes sense. But having to come up with those ideas, I don't think people can answer that so easily. Like, where does that even come from? Anyways, that's a philosophical point, not a
No,
technical one.
definitely. And that with the foundation they change, right?
Sorry.
That's where the fundamental knowledge is added, like
Yeah.
foundation knowledge
Yeah.
itself. True only.
Okay, so what else do we have for today? Okay, I've already covered all of these things. Right. By the way, this thing.
The interpretation will be very interesting.
Right. Let's come to the interpretations. Okay. Let me erase all of this because it doesn't look like I'm going to spend any more time on this. I've already covered these things. Right. So remember, this started out by talking about two different interpretations. One is thinking of this as a problem between two controllers or multi controllers taking actions at different time steps, which is what we've been saying so far. That's one way of looking at it. Another one is the previous idea uh, that it is one controller taking action multiple times based on whatever information it has. But both of those are roughly still the same things. So, another interpretation of this is in terms of communication. So, this seems like that's what is happening here. So, after taking the action, the new state got created, and this portion is the communication portion of the problem. If what was visible to this guy was actually the same as x1, this wouldn't have been an issue, or it may have been slightly easier. It may still be an issue. So let's talk about that. One second, I do not recall what are the points to be considered now. One second. Hmm. So now let's say, instead of focusing, before we get to the interpretations, let's look at a few variations of the problem to understand it better. So let's say we are talking about the situation where the cost is modified. This is a modified cost. We're only looking at the second component, what is to be optimized by controller 2. Now controller 2 is only going to try and minimize this quantity, and this minimization, it can still focus on gamma 1 and gamma 2, but this minimization can be thought of as x1 minus y, x1 minus u2 and a square of that. And for u2 we already know what this means. For u2 it just means this is the kind of problem we're solving. It's a simple optimization problem. It's u1 who has a choice here. So let's say the action taken by this is u1, the action taken by controller 1 is such that it cancels x0. So whatever is visible to the second controller is just noise and nothing more. So we know that x1 is going to be a function of x0. So let's say this is the scenario. If this happens, then x1 is just 0. So this term doesn't exist. Now, if we take u2, yeah, if we take u2, we know u2 will be something that depends on x1 and the noise, and x1 is already 0. So it just depends on noise. So let's say u2 is such that it's just a constant 0. In that case, the expectation just reduces to 0. But this is for the modified case. And if we are dealing with a problem where, actually, since we are talking about quadratic cost, it can obviously never be, it cannot be less than 0. So this means that gamma 1, gamma 2 are definitely optimal strategies. And they're both clearly linear.
Only if real number is used.
Yeah, I mean, that much I think we're by default assuming. If
Yes.
that's not the case, sure, it's a different scenario altogether. But see, here when we are talking about this, we are strictly taking a scenario with a modified cost. If in the same problem we were to introduce the same cost, okay, right, if in this problem we were to add the other cost, so then what will happen is, let's copy this. What was the actual cost? It was, right, u2 is still fine. The minimization is of this quantity. u2 will still have the same form. Let's say we take the same scenario as previously. So in that case, what we'll get is u1 has some value, so it's some expectation of that. So it reduces to just expectation of x0 square, or the variance of the Gaussian x0 that we're considering, whatever that value is. This plus x1 is 0, so it's 0 minus u2, which we are also assuming to be 0. So this term doesn't exist, but this one does. So for our action, so for this particular policy, if this is what we are referring to as our Witsenhausen's main J star, then we see that this time J star is some k square x0 square. Now, if this x0 is large, if there is a lot of variance in the problem, then J star is definitely not 0. But okay, for this policy, let me call this policy as mu. It might be possible, so just a claim, it might be possible that there is some other policy for which this J star actually turns out to be less than this J mu. So we managed to get a bound, but that's about it. Point being, what was clearly an optimal policy in the simplified modified cost problem is not the same in the original cost problem. So this is the original problem. So this is suggesting that the policy U star, which consists of gamma 1 star and gamma 2 star, this could be non-linear, because linear, one of the linear strategies is definitely not working. In specific situations it might end up being linear also, but that's not in general necessary. Okay, so now let's
But if somebody choose, maybe as of now I'm just thinking, if
mhm.
somebody choose a particular cost, again it will become linear because it's like for a particular cost type, it is properly coming.
Mhm.
When you add something, it is coming non-linear. But suppose if I add one more element, maybe it will become again linear.
Yeah, so it's getting dependent on the cost, but the
Yeah.
point still remains, right? It was assumed, or it was already believed, that it will always linear,
Oh,
search over linear strategies was enough. That's why it
oh,
was optimization over actions in a simpler sense, because we had already chosen a function class for the gammas in the original scenario. But in non-classical information structure, it may or may not hold.
okay.
Right, so yeah, this is the same point. Hmm. Okay, now let's think about what would happen if in the same problem we took the classical information structure. So in the original Witsenhausen's problem, if we changed the information structure, changing the information structure just means adding the y0 in the other one. Then the overall problem becomes the following. Yeah. Now notice here, this will be some function of I2 and not a function of gamma 1 anymore, which makes it possible to solve and simplify. Um, okay, I think this is the suggestion. Let's try out what this suggestion means. This is the suggested policy. Suppose u1 is just taken to be 0. So this term goes away. All that is remaining is just this one. And now this term, this is x1. And because we have taken action u1 to be 0, x1 becomes the same as x0. And this y2 c is okay. Let's write that down. Now gamma 2 is something which is x1 plus x0. This is not true. You're trying to find out what is the mean of x0 given x0. So that is the actual realized value of x0 itself, whatever that value is. So this is what we get. And if we plug this back in, k square gamma 0 plus expectation over x1 minus x0 whole square, then this ends up being 0, right? The first term is 0 because u1 is 0, and the second term, we know x1 is equal to x0. That's what we got as the optimal of this one. And since we managed to say that we've reached the value of the quadratic cost to be 0, means this is definitely optimal. So what happened here is a very simple linear strategy. Let me write down this part more carefully. These are both linear. So a linear strategy managed to work. It's very much possible. One second. So a linear policy became the optimal policy. This does not mean that there can't be a non-linear optimal policy, but because we managed to find a linear policy that was optimal, it's not necessary that we look for a non-linear one, because we know this can't be minimized any further. We've already reached 0. So the point that is to be made here is, if we are dealing with the original Witsenhausen problem, but in a classical information structure, we would basically end up coming back to the original scenario itself, the standard LQG problems, where linear policy would be the optimal policy, would be one of the optimal policies. And if that is the optimal policy, it's enough to search over linear actions and just choose the best one from there, because it does exist. So if it exists, we'll find one. Okay, so what we are trying to understand over here is, if the cost was modified, it is possible to get a linear policy which is optimal. But if we used that same policy which was optimal in the modified cost, it may not be optimal with the original cost. It would still give us a bound, but it suggests that the the optimal policy, the optimal actions might actually be non-linear, and still the search is on which particular class of functions should it be. Again, if we were to stick with the original Witsenhausen problem but with classical information structure, then linear is enough. So all of these variations of the same problem are telling us the cause of the reason why we are no longer able to find a linear optimal policy is because we are not in the classical information structure anymore. If we were, we would find one. If the cost was different, we might find one. In the particular example, we are not able to find it because the optimal policy most likely lies somewhere else. So now let's come to the one possible interpretation that was discussed in the lectures also. Okay. For this, it's good if we refer to the diagram. One second, I'll just copy the diagram. So one way of thinking about this is, um, the first controller is the one who makes actual observation about the state. So it knows actual x0 because it is taking an action. So, and since we are in a linear setting, it also knows x1. Clearly, it wouldn't know u1 or this component, but up till here, it knows all of it. So you can say that this particular controller is actually the agent who is in the field, who is part of the component that is collecting information or collecting the sensor data. Once it has decided what kind of information to collect and pass on, and what kind of action to take on the collected information, then it passes it on to the other controller. So it affects it, then passes it on, that gets some noise added to it, and that finally reaches the other controller. And the other controller can be thought of as some supervisor who is only looking at just the information it has got. It does not have access to what is happening in the field. So you can try thinking of the traffic example that you suggested earlier. So whatever
But
yeah,
in that case, delay was there, not noise.
delay was there. Let's say there is some noise also in the system.
For noise, we have to introduce the something else which GPS or Google Map can't track. Maybe rain.
Hmm.
Yeah, because the app can't say that due to rain it is coming or something. That rain.
Sure.
So it's
Some
heavy rain comes, so most of the bikers and they will stop in the corner and they'll create the traffic.
correct. Possible. That's a valid example. I think that's it's fitting here very well. So the
And then
inf.
one more,
Hmm.
okay, since it's a Gaussian noise, I want to make one more possibility due to rain. Maybe biker is not so, but waterlogged.
Hmm. Hmm. Waterlogging is a more natural one.
So two possibility. One more possibility I'm thinking like can we make a kind of Gaussian thing? So event one, event two, event three, and then anything can happen.
Ah, sure. It's okay. You don't have to map an exact real world problem to a Gaussian setting or the exact one we're talking about. As long as the analogy holds, we're okay. We're
Mm-hmm.
okay to go further with the interpretation.
Mm-hmm.
So, whatever information is available to Google Map or the app that is creating an algorithm and giving you only a part of the information, that is like the field agent. The other agent, who is the driver, is deciding what to do with that information. It may not know that there is waterlogging somewhere, maybe there is a pothole, maybe an accident happened, whatever. It may not know all of those things unless clearly stated by the particular app it is using, right?
Correct.
In
Correct.
that scenario, there's a difference between the two controllers. One controller is a part of the field and knows what is happening there and is able to actually even affect the states, but the other controller doesn't have all that possibility, all that control available to it. So one possibility could be, depending on this kind of a problem, maybe this controller can choose u1 to be very high, so high that the original value of x0 is not important at all. Then x1 is going to be pretty much u1 and some noise added to it, but the effect of noise maybe, what is it, maybe u1 is so large that the variance of the noise also doesn't affect y1. So ultimately y1 manages to estimate the action. If it manages to estimate the action as best as it could, and it takes its own action accordingly to minimize that effect. So we could have x2 to get completely eliminated. But because we are talking about a situation where y1 is big enough to cancel the effect of noise, this component this component in the cost will be quite large, and we will not be able to ignore this.
But cost is in our hand. We can reduce k. K tends to zero, and it is fine.
No, no, let's say we're restricting to one value of k.
Okay.
We're not changing the value of k to fit our problem. Okay, so that's one possibility of what it could have done. And that's one way to think about what this problem is trying to do.
For the Google Map solution, the solution is coming like a policy of a controller depends on the app decision or app information, like Gamma one.
It does.
So yeah, it does in real life. It does. Absolutely right.
So, by chance, suppose what happened was, um, there was some server problem with the Google Cloud and all of that. Because of that, the traffic signal, the color, sorry, not the signal, just the traffic color of one particular road didn't get updated in the last, let's say, 5-10 seconds. Even though the traffic may have moved, meaning the color should have possibly changed from orange to green now, but the app didn't get updated. So as a user, I'll not know that. I will not have an information about whether the information that I'm seeing is updated or not, or whether there's some extra noise in it or not. So I will be taking my action based on what I see. So I might end up not choosing that route just because it shows orange, and I might get stuck in traffic. I might take another route, which is where the traffic might actually be, and same problem may have happened. So taking the wrong route happened because I didn't get the perfect information or the complete information I needed to make the decision. But whether I get the complete information is not in my hands at all. It's in the hands of the previous controller, the controller in the previous step. So it's like you can't ensure that a problem like this can be solved where both of the controllers are trying to separate their problems and solve for the best case separately. They have to try and do something together, only then it'll work.
Actually, I have seen this because,
Hmm.
like, not seen. Like, for example, one more example to on this Google thing,
Hmm.
like, the subway tunnel, right? So when you go to the car after rain, it is waterlogged, but Google don't know. Google will show it's a green, but when the car goes, it is full of water, so car can get stuck there. So what
Right.
nowadays you have to give a feedback to the Google, like there is some problem in the route, and then Google will update the path. So it's like joint optimization is happening there, like
Exactly.
communication from controller past, like second controller to one. Like, don't know, it's very fascinating after this.
Yeah, you've actually managed to get to the crux of it, because that's one way of thinking about Witsenhausen's problem. It seems to suggest that controller 1 needs to communicate either x1 or x0 to the other guy. Even though there is going to be a noise added, the choice of action should be such that it manages to communicate something to the other controller. Then there might be a possibility to minimize the cost in the best possible value, to the best possible value that there is.
Mm. And nowadays there's a feature like if traffic is slow, it asks like is there an accident or something. Google will ask, so you have to give reply no or yes. Based on that, I think this they based on this principle, the joint optimization of both.
Yeah. See, if you think about it in a real world setting, in the scenario where we're talking about traffic and Google Maps and all that, it makes sense that they should be taking feedback from the controller
Yes.
who's actually going to be using their app to make their decisions. It should
Yes.
take that as review, as extra information, which can be of use to the other people who are going to be using it. It makes complete sense, but the fact that it comes up in such a model problem also is what is fascinating. And we can relate, like it um, where it might be possibly coming from, where the true motivation or the true inspiration lies, which is this kind of examples or this kind of works.
Mm, true.
Yeah. So this was one perspective, right? Where you're looking at the two controllers in a slightly different light. They don't have the same functionality, they have different objectives. This guy is only trying to estimate x1 based on the information it has to the best of its knowledge. But what x1 will be is something that gets affected by the control taken by the first controller. So if controller 1 does something smart and manages to communicate that to the second controller, that's where there might be a situation where the cost gets minimized. So, what this seems to be suggesting is another perspective to this problem is to think of it like a communication problem. So, now thinking of it like a communication problem is still not perfect perfectly. It's not like a perfect analogy. There are gaps, because if you were to think of it like a communication problem, you would basically be saying that this part up till here, yeah, up till here is the transmitter, or transmitter deciding what to do, the optimization problem of the transmitter. And then after the transmitter has done whatever it wants to do, the receiver receives the information and decides what to do with that information, basically trying to decode it, for example. But in a communication setting, the objective would be to try and estimate x0. The receiver would be trying to estimate x0, given whatever information it saw, so given y1. But in the problem that we have, what we are trying is the controller 2 should be able to estimate x1 given y1. So there's a slight difference, but still, it's suggesting that we can think of non classical information structures as something where there might be communication required, or there might be implicit communication happening. Uh, that y1 is such that it manages to communicate something useful to the receiver. In fact, there's the one possible solution is very simple. So let's say y1, sorry, gamma 1, gamma 1 is based on x0, right? So let's say this is just a very idealized situation. So let's say x0 is greater than or equal to 0, or the other way around. So gamma might be like, okay, if x0 is positive, make it some big positive number, else take the action to be some big negative number. So what the controller 1 did is, this is I think this was not there in the lectures, but this is one possible way of thinking about it. So what is happening here is it has managed to convert all the information about what is x0 to just whether it is greater than 0 or not. It has converted into a binary situation. And estimating a binary situation is still easier than estimating something more than that. So now x1 will be x1 plus c if x0 is greater than or equal to 0, else, and let's say this C is a fairly big number.
C is very big number.
Actually, C is large enough.
Okay.
So it converted this problem of estimating x1 from x1 with some noise to just finding out which of these two scenarios it is. Now it's just a binary problem, right? All the estimator needs to do is whether it's here or here.
Hypothesis testing with different mean.
Yeah. So this became slightly easier. The estimation problem became slightly easier. But what it's actually doing is it's giving some kind of information. It has managed to encode some information about x0 and it is passing it through the action. It's not passing x0 directly or negative of x0 directly, which is what we had seen earlier. It's not doing that, but it's still passing some information. But notice the kind of function that we're using here. It's so gamma 1 given x0 is some sort of a step function. That's definitely not linear, right? So now it might boil down to finding the correct C which could optimize it, but that's a different part of the problem. All I'm trying to point out is it has converted the problem, which had this non classical information structure, to figuring out a way to pass on some information. Controller 1 is just trying to pass on some information to controller 2. That's all it's trying to do now. What that information is, how to decide whether to take the break at, take the splitting of the step function at 0 or some other value, or take a step function or take some other function, that is all a different part of, that's different information. But it's possible to communicate something to the other one so that this estimation becomes easier. If this estimation becomes easier, then the difference between x1 and gamma 2 star, this was gamma 2 star, right? Whatever it depends on. If the estimation is as good as possible, this would reduce significantly. So this becomes a trade off. It's like finding the right C, sorry, this right C, so that enough clarity is given to the estimator such that this reduces and also the k square times this square term is as less as possible. So the takeaway message here is non-classical information structure would likely require non-linear optimal actions or policy, and there may be some implicit communication. I am assuming the details of how the problem is solved, Witsenhausen's counterexample, how did they deal with it to whatever extent they managed to, might be covered in the next lectures and so on. Yeah, do you have a doubt?
Uh,
No? Alright, let's quickly just recap what we did today and then we can pause. What is this? This is just some examples. We've already covered them. Okay, so we started by taking a recap of pretty much what we have done in this course, focusing specifically about the things that we learned from LQ problems, LQG also. Then we said that one of the underlying assumptions in those problems was that there is a special kind of partitioning in the information, meaning information at current time step will be more than or equal to the information in the previous time step. Whatever that information is, it will just be more or equal. It will be at least the same as the last one. Such an information structure, or what is known to who, is called as classical information structure. Then we saw, we talked about a few different interpretations of it, or what this classical information structure means. It means either there is infinite storage available, that all of this information is getting stored, or that there is perfect communication happening between one controller to the next controller. Then we saw this example where the standard control problem can be actually thought more carefully, and this can be thought of as a few different optimization problems which are typically solved separately, but if they're solved together, it might be possible to get an even better uh, decision, a joint decision for all of that. And this is an example, a real world example of non classical information structure. And then we saw a few examples of what does it mean for IK to be classical or not classical. We saw quite a few examples to understand that the core is just this condition. The current information should be more than or equal to the information in the previous time step or to the previous controller. That's about it. Then we saw what was the Witsenhausen's counterexample, what it's trying to do. We focused on the different components of the problem. So this particular problem had two components in the cost, and because of these exact two components is the reason why the problem is coming up. And we saw that the action that is to be taken by controller 2 will depend on what action was already taken by controller 1, which makes this problem highly nonlinear. So gamma 2 is something that depends on gamma 1, which makes it very nonlinear. Then to understand this better, we took a situation with a modified cost, and we saw for that modified cost there is a linear optimal policy that gives the cost to 0. But this is in the modified cost. If we were to take the scenario with the original Witsenhausen cost, meaning we add this extra term and use the same policy from the last one, we see that that policy ends up leaving some residual value, some case square multiplied by the variance of x0. And this can actually be thought of as a bound to the optimal value in the Witsenhausen problem. And since this was a linear strategy, it's very much likely that the optimal strategy in Witsenhausen would be nonlinear. In fact, to understand that even better, we took this same problem of Witsenhausen and just changed the information structure. We took classical information structure in that, and we saw that there is one policy, a linear policy, for which we get an optimal value. Meaning it's the non-classical information structure which is what changes the whole scenario, and the optimal strategy may, or the optimal action may or may not be linear. And then we talked about different perspectives of this. One perspective is thinking of the first controller as someone in the field agent, and the other one as a kind of a supervisor, meaning they have different information and hence their actions are supposed to be different accordingly. Or this can be thought of as a problem between transmitter and a receiver. The analogy between this problem and transmitter and receiver is not very concrete, because here in Witsenhausen the focus is to estimate x1 given x1 added with some noise. In a transmitter version of it, we would actually be trying to estimate x0. The receiver would be trying to estimate x0 because y1 is the action. So this suggests that this non-classical information structure could have some relation with implicit communication. And I gave a slight idea as to how can one construct gamma 1 and reach a situation where the cost might get reduced to an extent. And this gamma 1 that I've shown is something that is non-linear, and it seems to be signaling to the other controller what were some information about the original information, the original x zeros. So the point here to keep in mind is, if we are dealing with non-classical structures, even in LQ problems, we cannot expect linear optimal strategy or linear optimal action. It might be non-linear, and there may be some implicit communication required to get optimal actions or optimal policies. And in the next lecture, I think it'll be few more modifications of Witsenhausen's problem, and then finally what is understood about it and what information is taken from this paper and carried forward in other problems. So yeah, with this I've covered this week's tutorial. Any questions?
Yeah, one question.
Hmm.
In the lecture, sir was telling about decentralized control. He used the word, but he never came back on that word when he was
Oh.
using this. Why so?
Uh, Decentralized means that there is no central unit telling each controller what to do. For example, a situation like this.
Mm-hmm. But in general, also normal system will be same only, right?
The
No,
idea is same. There is decentralized just means that there is no central unit telling each controller what to do.
or is it like central information is not present
Or central information is not present.
where everybody is aware? No, no, I'm just trying to make sense. I observed this, sir use this word, but he never came back on.
Yeah, it's a word better not to get into too much details of. But this example, Witzenhausen's example, is actually a decentralized control example.
Okay. Okay.
Yeah.
Yeah. Thank you.
Yeah.
Bye.
Thank you. Bye bye.